All right, and we are live. Welcome to a very important day in your data science, not data science, data structures career. We're going to be learning more coding with linked lists today. And since the next competency exam is going to be on linked lists and you have to know how to code them, today is a very important lecture. So, how do we do a linked list? Well, we had this before that we started with. You know, we have a list class, we got an X pointer and a previous pointer, and we're holding data, and then or that's a node. And then the list itself holds a pointer to the head and the tail and keeps track of the size. So, in computer science, the notion of an invariant is really, really important. An invariant means that you're always guaranteeing something to be the case. So no matter what happens, you push, you pop, these invariants are always going to be true. And if you forget even like one of these in one place, your class might break entirely, right? So like size should always hold the size of the list. And if we had like one of these branches down here that returned earlier or something like that before doing the size minus minus, then that could cause, you know, our code to see if the list is empty, to fail, and it might seg fault and things like that. So there's a lot of precision that takes place in computer science. You need to be as close to 100% as accurate as possible, and you need to test your code thoroughly as possible. You need to do every combination of pushing and popping and inserting and deleting that you can think of in order to verify that your code is correct. And if it's not, then you need to figure out what the hell happened. Okay, and address sanitizer is your friend, and so by default, G++ is aliased to use, maybe not on me, become when, yeah, for you guys, not for me. For you guys, it is aliased, G++ is aliased so that undefined behavior sanitizer and address sanitizer are turned on. And so that is like a real-time checking of your code to make sure that you are not dereferencing a deleted pointer or double deleting or any of the other problems that going out of bounds, fandangoing through core, all these kinds of things. Address sanitizer is your friend, and it is a really, really nice tool. So when you guys go to another institution, which I hope you all will, transfer to a UC maybe, or Stanford, or you know, wherever, it doesn't really matter, Fresno State. It's all good. Remember this, because as far as I can tell from all of my discussions with alumni at other institutions, none of their professors either they don't know about this or they don't use it. And that's problematic, because these are really nice things for students. They will help you a lot and find your bugs. Whereas a lot of students, they write bugs and then it just doesn't work and they don't know why. Address sanitizer in particular, when you're working with linked lists in particular, is a really nice tool to have. Okay. I have it turned off on my alias because I don't need it. I don't write bugs. Actually, it's just to speed up the compile time. It does actually slow down your compile time a little bit. And so I turn it on when I need it. All right, so main.cc. So we've got push front, pop front. Some people tried using this code that I put here in their superhero mart assignment, which was not needed at all. The standard library, the whole point of superhero mart was to teach you guys about the list, std list of list, and how to use it. In particular, the splice function, which can glue two lists together in order one time. So if you have a billion elements in one list and a billion elements in another list, you can glue them together into a list in order one time, which is really, really fast. Something you do with a linked list that you cannot do with like a vector. Okay. Does it slow down compile time that much? Let's find out. So time, G++, main.cc. So that took half a second, and then which compile. So about 0.8 seconds. Yeah, it's noticeable. It's a noticeable lag. Does Splice clear the list you're copying over? I believe it does. I believe it invalidates the previous list. So don't use it after you splice. So it's a concept called moving. I don't know if it's the right time to have that lecture. There's something called std move that's really important, and R value references and stuff like that. But we got a big topic today. Remind me to talk about that later, though. So we got a lot of stuff to go over today, and that's the code to do a doubly linked list. So the hardest part of a linked list is actually not what we did here, because adding to the front and adding to the end and deleting from the front and deleting from the end is actually not bad. You just have to make sure you think of all the different invariants, right? You have to keep all 4 invariants in your head at all times and enforce them. And if you forget any of them at any time, your code's gonna probably break. I think list just lets you make the list, right? So why do we need to make a list class if it's included in list? Great question. So the inclusion of especially singly linked lists into this C++ standard was actually fairly controversial. And the reason for that is that a lot of the benefits of a linked list come about when you actually have the pointers to them. There's a lot of like pointer tricks you can do and things like that the list class does not expose its pointers. It is not what's called an intrusive linked list class. When you use std list, you don't have access really to any of the pointers on the inside of it. You actually don't know if it's being implemented using pointers at all. It might not be. It could be done using like a combination of like arrays and pointers and or whatever. Like you don't know how it's implemented. There is an array list. In Java, the vector class, there is a vector class technically, but nobody uses it. They use array list, and it implements the list interface of like being able to push and pop and things like that. But behind the scenes, it's an array. It's a contiguous block of memory. And so when you have a list like this, you don't know you don't have access to the internal pointers. And so sometimes there are tricks that you need to do with the internal pointers that you can't do with this std list class. However, you will find that most people can't write a list class without bugs. And so using std list is preferable because it doesn't have bugs in it, at least not that I've seen. Okay, so and also the reason why we write these linked lists, Emma, to answer your question, is because you understand them a lot better after you've written them. So for the EU4 assignment, you're going to have to start really understanding pointers, not you in particular, Emma, just everybody in general. You have to start understanding pointers and the use of the arrow notation, like that will return heads data member value. That returns tails member value. Getting into the habit of checking for pointers being null first. It's like if we don't have that null check there, and we try calling front on an empty list, then Ada, then it will segfault. Okay, if you ever dereference a null pointer, if head is null, can you turn the light on behind me? I'm kind of like in shadow here. Thank you. If head is null, in other words, it's an empty list, and you call front on it, it'll segfault. It'll crash your program. And so you need to learn to get into the habit of always checking for things being null first, especially when we get into binary search trees. Binary search trees are linked lists with also 2 pointers, but they don't go forwards and backwards. They both go down, one to the left, one to the right. And you're going to write one of those too. And if you don't get into the habit of checking for null pointers, you will never be good at using pointers. And pointers come up. They come up. They are used in computer science. Modern C++, you can get away with having to use them most of the time, but they still come up. And in CSI 45, they're using pointers right now. They're the midterm right now. It's ending in 2 hours. So there's probably a lot of students on the server right now. Let's find out who's waiting to the last minute to take the CSI 45 midterm. Yeah, there's a lot of them. How did I know? How did I know? What does return open close curly brace do? Where do I have that? Ah, right here. So that, do you remember how we talked about how you can return an anonymous variable? Right? So we're returning a string. And so what this is going to do, you can't just return nothing. You know, that doesn't work. And so this is the same thing as saying return string initialized with nothing. Okay. So that will return empty string. But this works with all data types. So if I were to change this to be like an int or something, then this would return 0. So if you ever need to return a default constructed value, open close curly brace is the way you do it. Okay. All right, so let's see, first of all, let's see what a segfault looks like. What do we got down here? Main, got a wedding list. Yeah, we don't need this stuff on consts anymore. So we got a wedding list. Let's just call, let's push Lester onto the list, and then let's pop. He's getting disinvited now. Pop back. He gets disinvited, and then we're like string whatever equals wedding list dot front. Okay. So we're going to get the first element of the list. How many elements are in the list? None. Okay. And so if I come up here and I take out that check, I think I did. No, I didn't do it. If I take out that check, let's try coutting it, right? Cout, whatever. If I take out that check for a null pointer, comment all the rest of this out. So do you guys understand what's happening here? I've got a list. I've added Lester to it. I've taken Lester off. And then I get the first element of the list. I technically don't even need to do these 2 lines; they're just there for demonstration purposes. Then I'm going to try outputting whatever was returned by it. So if I do this, yeah, we are going to use templates later on. We get a segfault. Okay. So, what is the segmentation fault? So in a computer, there are different segments of memory. And so the operating system knows where your program is in RAM. The actual numbers don't matter, really. And the actual numbers are lies anyway, so they really don't matter. But let's draw... Where's OneNote? So let's try and understand segfaults a little bit better. And by we, I mean you. New page. This will be 2.19.21. So what happens when a program is running? There's you have like your a.out, right? And this has a bunch of object code in it. Object code looks like zeros and ones, you know, kind of like this. And the CPU will kind of interpret that to mean like, okay, that's an add, and that means add 0, and that means, you know, 17 or whatever, you know. Object code's just zeros and ones, right? It's the, you know, result of the compilation process. So you got this a.out, and it's got all these zeros and ones in it. But what happens when you run a.out? When you say run a.out, what happens is your Unix shell, the command prompt, opens this file up, and it's in something called ELF, ELF, right? Because computer science people are D&D nerds also. And it stands for executable loading format. And so there's a certain file format actually to all this object code, and it tells the operating system how to load it into RAM. And what it's going to do, it's going to set up a stack up top here, at the top of memory. Technically, the operating system is either up here or down here, depending on your perspective. And it loads what's called the text or the code segment down here. This is where your program is. And then there's a couple other segments, read-only data, and just call it BSS, which is where constants go, or sorry, not well, RO. RO data is the read-only, but let's just say globals go here. So all of your global variables go into the BSS. What does BSS stand for? Nobody knows. It's a mystery. And then above the BSS is what's called the data segment. And what happens is every time you call a function, the stack pointer moves down. You have something called a stack pointer. Yes, there are pointers in computer science. And so when function f calls function g, which calls function h, the stack pointer moves down, stack pointer moves down, stack pointer moves down. This is where all of your normal variables live. When you say integer x, you know, if you're inside a function void h, you're inside a function h, and you just say integer x like that, when you call h, it moves the stack pointer down, and it moves it down far enough that x is going to live right there. And then when you return from h, when it terminates, the stack pointer moves back up. And so it has the effect of allocating and unallocating your variables automatically. All of your regular variables like ints and doubles and all that stuff, all of them appear on the stack. And so when you call the function, it allocates enough memory for all of those variables. And then when it returns, the stack pointer moves back up. And then when g returns, the stack pointer moves back up. Then when f returns, the stack pointer moves back up. And you're back in main, and all of main's local variables are in here as well. So, and then main calls another function, the stack pointer moves back down, the function's returned, the stack pointer moves back up. That's why these variables, like int x, like the normal variables you have, they used to be called automatic variables. You used to be able to say auto int x. And this was how you could do it back in the 1980s. And that would indicate that integer x was an automatic variable, which meant that it would be allocated on the stack. As it turns out, if you leave out the word auto, it's allocated on the stack. So nobody used it because it was pointless. But the auto keyword was in the standard. And so the C++ standard people don't like breaking old code. And so what they realized was that they could use that keyword that was reserved. Nobody could, you know, use it for any other purposes, and do this auto x, and auto x equals 5, and that's where the auto keyword came from in modern C++, was because it was already a reserved keyword. But the old use of the word auto meant it was stack allocated, but just nobody used it because it's stack allocated if you don't use it. So why would you use it, right? And so auto x equals 5 is modern C++, and this will deduce the type of x from the right-hand side. So because 5 is an integer, x will be an integer. And so that's a new use for an old keyword, which meant stack allocated. Now, what happens if you allocate too much stack? What if void h here, what if it doesn't just make one integer? What if it makes a lot of integers? How far down does the stack pointer move? If we're going to allocate 1 billion integers, how far down is that going to try and move the stack pointer? Changing it to that did not break legacy code exactly, because the way legacy code, anybody who did use it would have written auto int x, and what they changed it to was auto x. So this was not legal before, so nobody used it in any legacy code. So they were very clever about it, and they like reusing old keywords in new ways so that they don't break old code. They care about that actually quite a lot. It still happens, but they do care about it. So if I'm going to try allocating 1 billion integers, how much RAM is that going to allocate? Is legacy code the code that's passed between people using it? No, it just means it's old. Some people have been working on the same code for 40 years, you know, like WebAdvisor. So how much RAM is this going to try and allocate off stack? If I just have a function named h, and I just all I have in h is int x square bracket 1 billion. I'm not counting how many zeros I have there. It's a billion, let's say. How much RAM is that going to try and allocate off of stack? Anyone know? How big is an integer on our system? On most systems. It is not 8 bits. An integer is not 8 bits. A character is 8 bits. An integer is 32 bits. So it will allocate 4 bytes per integer, and so 4 bytes per integer times 1 billion integers means this will allocate 4 gigabytes of RAM. So there is a boundary as to how much stack space you can allocate. And if you cross it, if the stack pointer moves down below that invisible barrier there, you get what's called a stack overflow. Which is the name of the most popular computer science support website in the world. So if the stack gets too big, it will overflow. And you can get this in 2 ways. One is you make an array that's too big. If you just make a regular array that's too big, it'll stack overflow. The stack's only about 200 megabytes on our system. So if you make an array bigger than 200 megabytes, it will stack overflow and it'll crash. The other way you stack overflow is you have a function call itself. Like if all h does is call h, void h, calling h, this will stack overflow because it'll keep moving the stack pointer down further and further until it exceeds the stack boundary, and you will seg fault and crash. What is different recursive then? I don't know what that means. If you have an infinite recursive loop, you will stack overflow. Guaranteed. Unless the optimizer like does some hijinks and optimizes it away. Optimizers do crazy things. They're really cool. So if you allocate too much off your heap, yeah. So when you call new, every time you call new, that is going to allocate memory off the data segment. The data segment moves up, and if it exceeds whatever your maximum heap space is, then it also seg faults. And the operating system has boundaries for your code, and if you access code outside of those boundaries, you seg fault and it kills your program. Also down here below text, there is the Minefield of Doom. The Minefield of Doom. It's not the technical term. I don't know if there is a technical term, but I call it the Minefield of Doom because this is at memory address 0. And so if you ever try accessing memory around memory address 0, and quite a ways around it, because a lot of people try dereferencing null pointers, and the operating system manufacturers, authors know this, they've just blocked off a section of memory that if you try touching it, it kills your program. It's a minefield. You enter it at your own peril. Okay? So the data segment can't grow into the stack on its own. No, it will seg fault. It will seg fault. So the Minefield of Doom is down here, and that's why our program died. Okay? And all you see, though, is segmentation fault core dumped. That's all it tells you. So by default, Unix kills your program and just prints to the screen seg fault. You violated memory somewhere. Somewhere. I'm not going to tell you where. Somewhere. And to a computer science major, this is a very frustrating error message to get because you don't know where the hell your code is bad. You forget one line of code somewhere, and it seg faults. So, first of all, let's talk about core dumping. So dumping core is a cool term, core dump, right? And what it means is it's writing a copy of RAM to disk. So I think I might have it disabled. Nope, yeah, it's disabled right now. So unlimit core dump size. So this command here, I'll put it on Discord because it's actually going to maybe come up for you guys. That enables core dumping. So by default, I have core dumps turned off. The reason for that is because dumping RAM to disk eats up hard drive space. And the server does not have a lot of hard drive space. The new server, the reason why I was a couple minutes late starting today is because I was talking to Nico, and we're going to get a new server with plenty of hard drive space. Probably, I mean, not plenty. It's not. My PC here now has 27 terabytes of hard drive space. The server, the department server is probably going to have. It's going to be partitioned, so probably for you guys it'll be about a terabyte, which it's okay. So the current server has couple gigs of hard drive space, not a lot. It's a really small. 40 gigs, 40 available. So we got an 80 gig hard drive on the server right now. Just tiny. It's a tiny little server. So we're going to move from that to a terabyte. Still not enough for my taste, but better. Anyhow, so the point is if you run your program again, it'll now write a core file. Do you see that? So in order to get a core file to appear, you have to unlimit core dump size. I posted that on Discord. I'll pin it even, so you can do that. I know, yeah, Linode is a great service, but they don't offer a lot of hard drive space for cheap, for some reason. Considering how cheap mass storage is these days, you know. So, yeah, so the copy of RAM is only half a megabyte. It's not that big in this case. It can be bigger for bigger programs. So what is a core file? Let's try opening it up in Vim. Elf, look, Elf. Scrolling down. Some strings in here. Lester's in the core file. There you go. So what a core file is, it's an autopsy. It's an autopsy report. So the operating system very helpfully writes a copy of RAM at the moment of death. So when your program dies, it writes your program and the RAM to disk so that you can do an autopsy later and figure out what the hell happened. It's not as good as doing it live, but it's still useful. And so here is our first important learning point for today, which is using a debugger. Looks like the mind game. Yeah. So this is the debugger, the GNU Debugger. It was written by my boy, Richard Stallman, RMS, and since, long since been taken over by other people. He started Emacs and GDB, but he doesn't do any active development anymore. So, what happens when we run GDB? Let's take a look. I should probably compile this with debugging symbols on. So let me go back up here. And last compile. Nope, damn it. Last compile. Damn it. Anyway, last G++. So, when you compile code, you want to turn debugging symbols on. Debugging symbols are enabled with -G. -G enables the symbols from source code to be put into the program itself. Oh, I had it on already. Oh, whatever. Okay, by default it does that for you guys already. So gdb a.out core, and there we go. Okay, so when you run gdb, you can run it with an executable without a core file, and then you can just run the program from within gdb. And you can step through the program one step at a time. You can print variables, all that kind of stuff. But if you run it with a core file, then it takes you to the moment of death. It's like in Iron Man 2 or 3, which is the one with Extremis in it. 3? Iron Man 3? Or 2? They all kind of blur together. There's explosions. Iron Man 3. Okay, so at the start of Iron Man 3, there's this drug called Extremis that is one of the reasons why Tony Stark was able to fight Thanos fairly decently. It was because he regenerates. So anyhow, so when they're developing Extremis, people would blow up. And so there's this explosion. Tony Stark goes there, and he scans the explosion, and he recreates it digitally. He creates a digital autopsy, and that's what we have here with this. And so it tells us our program terminated due to signal seg v, which means segmentation violation, segfault. And explains it to you in English here. So you segfaulted. That means you went outside of the boundary of memory. And it tells you that you crashed inside of basic string.h line 186. And a lot of new programmers' instincts here is to say, there's a bug in the standard library. The standard library crashed. No, your fault. So what happened? Backtrace. So BT or backtrace, you can write it out that way, it shows you, it's the same thing. It shows you where you were when your code crashed. So this is a backtrace of the stack. It's actually printing the names of the functions on the stack. So sure, it did crash within basic string.h line 186. But it crashed within a string. Error reading variable cannot access memory at address 8. Do you see how address 8 is very close to address 0? Like anything within the first, like, I don't know, 100 megabytes, I don't know how big it is, the Minefield of Doom, is off limits. And so it's trying to, so that's our problem, is that we created a string who is located at memory address, 0, basically. And so that was called from list front, which is inside of the file main.cc, line 33. Do you guys see I'm translating this into English for you? And that function front was called by main.cc on line 126. And then that's the same thing. You can either do backtrace that way, do backtrace that way. GDB has tons of abbreviations for things. And so if you want to print out variables, you can do that. You can go up a stack frame. So I'm now in that stack frame. Go up a stack frame. I'm now in the front. And I can say like print head. And head is currently null. Head is currently null. And so, yeah. So that's your problem. You're dereferencing a null pointer right there. Okay. So, yeah, you have to unlimit core dump size in order to get core files. And this will allow you to figure out where you were, what the, if I go up another level, I will be back in main. And I can print wedding list dot size. Will that work? Yeah, wedding list dot size. It understands C++. So wedding list dot size is 0. So I am calling front on a list of size 0. Maybe that's a problem, And so using print, you can print the values of any variable, just using their name in C++. Find out what's going on. Okay. So this will matter when you guys are working with pointers because you're gonna segfault. It's gonna happen. The stream delayed or freezing. So to see history, you have to use unlimit core dump size. Yeah. Yep. Or let's see. You can probably put into your .cshrc file if you want. So you can put that into your .cshrc file if you like. .cshrc. So vim.cshrc, or there's an alias for it, of course, called vc, just short for vim.cshrc. And you can put that into your .cshrc file to just permanently turn core dumps on. What file? .cshrc. So that is a file that runs every time you log in on the server. So if I become Yoxthymer, and there's a alias, of course I make aliases for everything. There's an alias to edit it. And so if I wanted to put into here unlimit core dump size, log out, log back in, it will now be unlimited. All right. If I type in limit, you can see that core dump size is now unlimited. And you have 8 whole megabytes of stack space. It actually won't crash until you exceed about 100 or so. I've tested it. And so if I want to mess with Yoxthymer, I could always go fortune, pipe through, cow say, pipe through lolcat. And so now every time Yoxthymer logs in, it will print a random fortune for him, have the cow say the random fortune, and colorize it. So there you go. And if you want to remove that, edit your .cshrc file. It'll be a good exercise for you. What else can we do? So if I compile main.cc, or if you guys were to compile your code and you run it, you're actually going to see you're not going to get a core dump. You're not going to get a core dump. Why? Because you have address sanitizer turned on. Address sanitizer in some ways is better than GDB, some ways worse. There's no interactive element to it. right? When we looked at the core file using GDB, we can move up stack frames, print the values of different variables. Be like, oh shoot, that's 0. The size is 0 right now. Ah, I forgot about that. Address sanitizer though doesn't do that, but it is automatic. It will automatically give you a better error message than just seg fault, right? So it tells you in main.cc line 13, character 16, member access within a null pointer. So you have dereferenced the null pointer on that line, and so you can simply come into main.cc line 33, character 16, vim main.cc, line 33, and it takes you right to the line that crashes your code. So you don't have the ability to like print and go up stack frames and see who called you and print variables and stuff like that, but it tells you exactly where your code crashed. And it also catches things that GDB might not catch, like a double delete, things like that. So like a double delete is really bad. Or not, yeah. Let's just put a double delete in here. Nope. Last G++. See, didn't crash. But if we were to run this with main.cc, it's let's try use after copy. So cout copy points to copy points to get the size. Okay, so we're deleting a pointer, and then we are going to no member name get size. All right. Data. So in our destructor, we're going to delete a node and then print the value that it has. So this is called a use after free bug. Use after free. So you can't use a pointer after you've deleted it. You can, actually you can. I mean, this is what's so dangerous, is that with address sanitizer turned off, it actually works fine. Oh, the reason why I wasn't crashing was because there's nothing in the list, right? Okay. Good. So let's go back and put some more people in here. Okay. And so now, if I do a double delete, now it should crash. Abort core dumped. Free, double free detected in tcache 2. Not very helpful, but thank you for telling me. It did detect a double free, double delete, and it crashed. It threw an exception and crashed. If we did this with address sanitizer turned on, then it gives us a much better error message. So scroll up through this. This is a print of memory. Scroll up to the top, and it's use after free. Interesting. It didn't do the double delete. Use after free. Interesting. Let's take out the use after free. Oh, I guess that's considered a use. Interesting. Yeah. So, yeah, address sanitizer again will tell you where it took place in your destructor. On line 115 of main.cc, you done goofed. Okay. So address sanitizer is kind of like an automatic version of GDB and stuff like that. It makes development a lot faster. If, however, you need the extra detail of a debugger, it's a good tool to have in your toolkit. Muya, have you been using GDB at all in 45? No, not at all. Never. Yeah, GDB is life, 45 especially. because you don't have these same tools. There's no address sanitizer for assembly. Okay, so now if we do a use after free, like this, where we delete a pointer and then we use it, get some weird stuff. Didn't crash, just got some weird stuff. And so, got some weird stuff in here. So this is a problem, right? Because we've deallocated memory and then we use it afterwards. It might have worked normally. Like you can see the data is still in there, kind of, yeah. Might not work. This is just printing RAM until a 0 appears, basically. And, you know, this is not the kind of stuff you ever want to see come out of your program. The printing the contents of RAM, right? Like, not good. And if we turn on the optimizer, we might get different output. We're very firmly on undefined behavior island right now. And so if we turn the optimizer on, you know, maybe we get, look, this part here is a little different. Look at that, you know. So, yeah, you want to come back as quickly as possible if you make a trip to undefined behavior island. If we compiled this with address sanitizer on though, and notice how it didn't crash. It did not generate a core file. It didn't generate a core file. And so if you're going to do this in GDB, you'd have to launch it like this, GDB a.out. Oh, no debugging symbols found. So let's turn debugging symbols on, run it, no core file. So we just have to do this like a peasant and step through it. GDB a.out, and we're going to type, we're going to set a break on, we'll just set a breakpoint on main and type run. And so when you set a breakpoint, it'll run until that point. Break main, you can type in function names and it'll stop when it gets to that function. It's very useful. Because main is not actually the beginning of your program, believe it or not. And so you run until it gets to main, and then you can start stepping through your program using step, or if you want to step over a function, you use next. And so next, like this is a function call, right? When you do cout double left arrow endline, that's a function call. If I did step, it would go into the standard library source code for cout. I don't want to do that. I don't care. And so I'm going to hit next, which goes over it instead of into it. And I can hit next again, next again. It prints the list, next again, and I'm kind of going like this through the code. Oh, look at that. Okay, well that's where the garbage came from. And the debugger actually detected this, that we done goofed, right? And then the program's over. Okay. So better than that though is that's having to debug like a peasant, right? Because you don't have a core file to jump you to the right place. Instead, you can just use address sanitizer, compile main.cc, which turns on address sanitizer. And when we run it, address sanitizer detects the mistake. Okay, so you're reading start and start main.cc line 117. There you go. Then main.cc line 117, and there's your problem right there. Okay. So these are two common mistakes. The most common mistake though is dereferencing a null pointer, right? So if I dereference a null pointer, this code will seg fault guaranteed. And not like a used car salesman guarantee, it's actual guaranteed. This code will guaranteed seg fault. Okay. It starts off by setting temp equal to head. If head is null, then it will read from null, seg fault. If head's not null, then it will print, or it'll delete whatever is at head, and then it moves on to the next one. And then it moves on to the next one, then moves on to the next one. It never stops moving. Eventually, temp equals 10 points to next will become null, and then it will try accessing memory at null, and it will seg fault. So, So gdb a.out.core. gdb a.out core. And so let's do it with address sanitizer. Address sanitizer, segfault. You accessed memory address 20. Memory address 20 is firmly within the Minefield of Doom. And so you segfaulted on that line of code. Okay. So this debug, I'm going through all the different ways you can fail first, because when you're developing your code, you're going to fail. Wrapping your mind around pointers is one of the hardest things you're going to do. So you're just conceptually, this is actually the hardest thing you're going to do all semester long. Okay. And that's why I'm giving you all this support on how to identify your mistakes. And one general rule of thumb you should always follow is this. Always check for a pointer being null before you use it. Anytime you see that arrow operator there, make sure that there is an if statement above it that is making sure that it's not null. Okay. So yeah, a while loop is an if statement with a goto. All right, so let's write the hardest code that we have to write, and that is, let's start with one a little bit easier. Let's do insert. So, or actually, let's do search. That's a good one. That's a good one. So, let's do search, and so let's make an intrusive linked list. So an intrusive linked list is one where you get pointers to the internal elements. So we are going to return a node pointer, and we're going to call this function search. And we are going to search for a string called key. I don't know. Hardest thing in computer science is variable names, right? So what we want to do is we want to go through the linked list, trying to see if key appears anywhere within it, and if it does, we return a pointer to that node in the linked list. Okay. Oh, we can't. We can't do that, can we? Because node is private, right? Because that's proper design. That's a good way of doing this. We do true or false. We do that. So is find. Let's call it find maybe. So it'll return true or false if the key is in there. So we've put a wedding list together, and we're going to see if Edgerlin is still on the list or if he's been purged. We don't have search function, or we're using the list library. You're not using the list library for this one. You're writing your own. You got to write your own for this one. Okay. So last time you had easy mode. This time you get hard mode for linked lists. So find will return true or false. So how do we do this? Down here, let's just stub it out real fast. Return false. So we've got Lester Edgerlin, Chris Johnson, and Arrow of the Hills. And then we can see out dual alpha, which will print true or false instead of 1 or 0. Wedding list dot, what do I call it, find. We're going to search for Chris Johnson. So this code should return true, right? Because Chris is in the linked list. However, it's not going to work. And it returns false. Okay, returns false. And the reason why it returns false is because we have not written the function yet. Right. So Chris is in the list, but we're not searching the list yet. Would append work well in lists? Append, we have append. Pushback is append. Yes, yes, it does. Appending and prepending are core core functionalities of lists. That's what lists are good at. Lists are good at pushing and popping, appending or prepending, or deleting, or whatever terminology you want. Push back, push front, pop back. Adding and deleting to the ends of a list are very fast, or in terms of big O. Okay. So find is going to search. We're going to search for Chris Johnson. Right now we're just returning false. So let's do it for real. But back to OneNote. So every time we call new on a new linked list node, it's basically gonna, one of them is gonna appear here, and then it's gonna appear here, and it just kind of moves up and up and up in memory. But you don't know where it is. It could be down here. It could be over here. Like, who knows? You don't know what number of RAM, what RAM number you're at, and it doesn't matter. And RAM, they're all lies anyway. So what we do is we use pointers to hold those addresses in memory. And so after we've allocated three nodes, we've got every node has a previous, a data, and a next, right? So we have a pointer called head that points at the beginning of the list. We have a pointer called tail that points to the end of the list. The previous pointer on head is pointing at null. The next on tail is also pointing at null. You guys understand? There's nobody previous to us if you're at the beginning, and there's nobody after us if you're at the end, right? So null is 0. It's just easier to write. And then this one holds Lester Edgerlin. This one holds Chris Johnson. This one holds Aaron of the Hills. And then his next pointer is pointing at this guy. Chris's next pointer is pointing at this guy. Chris's previous pointer is pointing at Lester. Aaron of the Hills is previous is pointing at Chris. And there we go. So that is the state of our linked list right now. There is cur. Nope, there is no cur. This is the state of our list. It's got a head, a tail, a size. We got size. Size is currently equal to 3. There's 3 elements. Eek. There we go. So this is where we're going to be doing find. So what we're going to do is we're going to create a temporary variable, which you can call cursor or temp or whatever, and we're going to set it equal to head. So when we start off in our loop searching, we're going to set cur equal to head, and we're going to say is cursor's data, is it equal to the key that we're searching for, right? If it is, we return true. If it's not, then we say cur equals cur points to next, and cur then points to its next. So it's now pointing at Chris. We say, does cur's data match Chris Johnson? Yes, it does. Return true. If, however, we get to the end, cur equals cur points to next, it's pointing here. Cur equals cur, it's pointing here. Then we say cur equals cur points to next. Oh. There we go. Then it will be pointing at null, right? Then we're done. So that's how you know that it is not, oh my gosh. That's how you know that it's not in the list, is when it becomes pointing to null. We've gone through the whole list, we haven't found it, return false. Okay. So let's write that in code. So get the tablet out of the way. So node pointer current equals head, while, I can make this a for loop if I want to, whatever. While current is not null, or if I wanted, I could write it not equal to null pointer to make it more obvious to you guys, but just, that means while it's not null. Remember, null is 0, 0 is false, so I'll leave this in here for now, I guess. It's the same thing, it's just extra typing. So while current is not null, if current points to data equals key, so if we have found Chris Johnson in the list, we will return true. Otherwise, we move to the next one. Current equals current points to next. We move to the next node in the linked list. And if we keep doing this and we never get it, it'll become null, and then we return false. So that is a find function. Compile it. Run it, and you see that Chris is now found. If, however, we were searching for Prente, then it will not be found. You explain again how to interpret the arrow operator. Yeah, this is a really important learning point that you need to pick up. What this means is that is just like the dot operator. Okay, so it's essentially the same thing as current dot data. Okay, but you use arrow with pointers, you use dot with regular variables. See, member reference type is a pointer. Did you mean to use arrow operator? Okay. So in Java, they actually use dot for both. Well, they don't have pointers, but yeah, or everything's a pointer. They just use dot in Java. In C++, though, you have to use the arrow operator for pointers, and you have to use the dot operator for regular variables. Is the arrow operator similar to using this? No, but we use arrow with this. So you say this points to head, because this is a pointer to us. So we use the arrow operator with this, but it's the arrow operator just is the dot operator for pointers. Is this necessary? No. No, it's not necessary. Some people like coding that way. Like you'll see some people. If you want to return a pointer to yourself, you need this. Like if you have a function that returns a pointer to yourself, then you have to use this. In most other cases, it's never necessary. But like some people write like when they have a constructor, like they'll do like I don't know, and size, and then they'll say this points to size equals size. Like this is a pretty common at Fresno State. So they pass in for the constructor parameters, they use the exact same name as the member variable. And so you can't say size equals size, right? That doesn't work. And so it's this points to size equals size. So it disambiguates which size you're talking about. I hate that. Not that I hate Fresno State, just if you forget that this, then your code will compile, and it's not going to do what you thought. So that's why you see me writing this. It prevents that bug from happening. So I can just say size equals size, like that. That's how I do it. There's a lot of different coding conventions, and there's a lot of debate over what's better and what's worse. And I'm just giving you my take on it. I don't honestly care that much. I'm not. My main concern is you guys not writing bugs. I don't like writing bugs, and I don't think you guys should write bugs. And so if there is something like this that could lead to bugs, I don't like it. So. Well, the downside of my approach, Ephraim, is you have to come up with a new name, a new variable name. And coming up with new variable names is the hardest thing in computer science. So. Key. What does key mean? Is it a password? Yeah. There we go. Compiles and runs just fine. There you go. Okay, so I think technically Unicode is not defined in the standard, but it'll compile. So Diamond Hands. It's a variable name. All right, so there you go. From now on out, all variable names will just be emoji. Pushback poop emoji, or maybe that should be pop. Okay, so so that pattern of like this could be also done in a for loop. So this could be all done in one line. So the pattern that I showed you guys last time, use it here, and that would be for node pointer current equals head, as long as current's not null. Current equals current points to next. If per points to data equals, damn it, return true, else return false. Okay, so that do you guys see how this for loop is just the same thing as this? A for loop, when you have a for loop, this part here runs before the loop, like that. And then this is the if statement that will keep it from running forever. And then this part of a for loop happens at the very bottom of the loop. So at the very bottom of the loop, we do that. So this pattern is very common for traversing a linked list. Linked list traversal could be done using this pattern most of the time, unless you want to go backwards or something. Okay, so let's do insert. So let's do insert after. So it'll find. Let's do find, but like. Find, but like we'll call it insert after. Void insert after. So string I don't want to use emoji again. All right, so string key and string new data or something like that. Okay, so what we want to do is say, after you find Chris Johnson in the list, put Mr. Wolf. Oh no, he's already in it. Put Emma on the list, right? So for insert after, what we want to do is after we've got this list here, let's not delete these people. Yeah, push print list. Push front arrow of the hills. And so we want to say wedding list.insert after. So insert after Chris Johnson. So Emma is going to get an invite. Emma, okay. And so that will put her in the list after Chris. And so what we want to do is we want to go through the linked list, find Chris in the linked list, and then put Emma in between her and arrow of the... No, wait, Chris is at the front, isn't he? So let's see, it's Chris, then Lester, then Wolf. And so this would put Emma second in line on the list. So it'd be Chris Johnson, Emma Scandin, Lester Edgerlin, and then Mr. Wolf. Okay, so I wrote this in the wrong direction, didn't I? Oh, it should be Chris first, whatever. All right, so nothing, little eraser action. We'll fix it in post, don't worry. edit the YouTube video, so no record will remain of my mistakes. People won't think I'm perfect anymore. All right, so we'll just clean it up right now. So Chris is actually first because I did a push front. After that is Edgerlin, and then after that is Arrow of the Hills. Okay, so when I say insert after Chris Johnson, what we want to do is put Emma, Esther Edgerlin. Damn it, Emma Scandin is also an EE. Ah. Oh no! Lester's L. What am I talking about? Okay, never mind. Where's my coffee? Emma's initials are E. Lester's is L-E. Yes. Okay. Yes. Lester, Edgerlin is here. And then Emma is going to get inserted here. Okay. So we're going to create a new node for Emma. And what do we need to do? There's going to be 2, 3, 4, 5 things that need to be done. Do you guys list some of them? Remember, anytime you have to take your eraser, or draw something, like Emma's next is going to be pointing at Lester, right? That's a line of code. That's going to be a line of code. So what do I need to erase? What do I need to write? Each one of those things is going to be a line of code. And that's why I really like sketching out linked lists first before writing code, because every, if I, what do we got here? I'll just take the first one. Come on, let me select it. Let me select it. Let me select it. Let me select it. Oh, you're doing that again, aren't you? So dumb. So yeah, let's say Chris Johnson's next needs to be set to be pointing to Emma. So that is a line of code, right? Changing his next pointer. OneNote. Why are you so terrible, OneNote? Why are you so terrible? I'm clicking on you. I'm clicking on you. Like, this is like basic functionality, Windows. Come on. This is basic functionality. I'm not touching anything on my keyboard. I'm just trying to click on a button. Switch. Huh, it's not working there either. Cool. Well done. All right, well. Let's try relaunching it. Program your own OneNote. Yeah, no, ain't nobody got time for that. All right, so let's come back in here, and there we go. And let's see if I can click on a button again. Yes. Well, it's already selected. I'm not going to touch anything. All right, so Chris's next needs to point to Emma. Right? Emma's next needs to point to Lester. What else? Lester's previous needs to point to Emma. Wait, no, it's not that one. Lester's previous needs to point to Emma as well. And Emma's previous needs to point to Chris. So those are 4 things. Those are 4 things. What's the 5th thing? The new is actually a good point, Mr. Wolf. I had to take pen to paper, or virtual pen to virtual paper, to virtual buggy pen to virtual buggy paper. And I actually had to allocate Emma, right? So that is a line of code, right? We have to new Emma, and then we have to set everything up. So there's one more thing we need to do. Tail to null pointer? No, why is tail changing? Tail's over here. Why would tail change? Why would head change? Here. Yeah, we're good. Lester's previous, yeah, Lester's previous gets set here. Yes, we need to change size. So size needs to become 4. Again, anytime you find me erasing and writing something, that's going to be a line of code. Now, there's going to be some edge cases with this that we need to think about. The main edge case is, what if the list is empty, right? That's what you should always start with. Edge cases, list is empty. Need to handle that. Maybe we don't. I don't know. The other is we're inserting at the tail, right? So if we're inserting after arrow of the hills, then the tail pointer will need to move, right? If we're inserting at the end. So let's do it. Tablet out of the way again. Where are we? Find InsertAfter. Okay, so what happens if Chris doesn't exist? I would say just don't insert anything in that case. So I'm going to do something really bad here, and I'm just going to say if we can't find Chris, just return. Right? And this is actually this is an order in extra work we should do. But that'll also handle the empty list case, right? Because if the list is empty, it'll return false, can't find it, and so it's laziness. Our code is still going to be order in. We're just doing twice as much work as we should. This is probably pretty garbage, but whatever. Yeah, whatever. I don't care. So now, if we get past this point, now we know he exists, and we don't have to worry about that case, right? If you get past there's a filter, right? If Chris Johnson is not on the list, it'll just bail out. So once we get past that filter, we know Chris is in the list somewhere. And honestly, I should rewrite find to return a pointer or whatever, like I was going to do originally, and make it a private, but I don't care. It's fine. We've got time to refactor later. This isn't changing the Dego notation of my code. I'm just going to leave it for now. If not find key, segfault, turn off PC. Okay, I mean, if you want to do that. Return null pointer. Yeah, just return. All right. So, all right. So we want to go through the list until we find Chris. All right. So copy and paste this code pattern. So starting at the beginning, going to the end. If cur points to data equals Chris Johnson, now we found it. Okay. And yeah, so now what do? There's what were the things? There's 4 different pointers that need to be modified. There's a special case of the tail. We should probably check for that first. So so if we are the tail, if current is the tail, you can do that. Then we'll special case the tail. Otherwise, we're just in the middle of the list. Okay. So worry about that later. So because we know at least for the code we're writing right now, Emma is going to come in second in line, so we don't have to worry about it. Actually, it is. No. Okay. Yeah. She's not. Okay. Okay. So what are the 4 things? There's 4 pointers that have to change. Chris's next has to be set to her. Her next has to be set to Lester. Lester's previous has to be set to her, and Emma's previous needs to be set to Chris. Okay. And then size needs to update. Those are the 5 lines of code, and 6 counting the new. All right. So first of all, we need to new the list. So node new person or whatever is equal to new node passing in. What is the order of the constructors? It's data, then next, then previous. Okay. Data, then next, then previous. Okay. So new node passing in data, which is going to be new data. So we're saying store Emma in the list. So we're going to pass that to the new node. So it'll be retained. Emma's previous will be our current pointer, right? So cur is currently pointing at Chris. And so her previous is going to be set to Chris, and Emma's next is going to be set to Lester. And so that actually just saved us 2 lines of code because we don't have to set our pointers separately. We can just do it in the constructor. So Emma's previous and next are both set. Did I have that backwards? I have that backwards, don't I? Yep. For whatever reason, I put next first, then previous. Unusable code. All right. There. So her next is set to our current's next. Her previous is set to our current, and then we just need to clean up the 2 pointers on either side. So Lester, who is another word for Lester is current points to next. His previous is that going to explode your brain? Lester's previous pointer is set to new person, and our next is set to new person. And we're done. So this may cause your head to explode. I don't know. Current points to next is currently Lester, right? And so Lester's previous pointer is set to be equal to the new person, and our next pointer is then set to be the new person, right? Don't do these in the opposite order because it's changing the next pointer, right? Is there a limit to how many arrows you can string together like that? No. In general, though, doing more than like 2 layers of indirection like this will absolutely cause people's brains to liquidify and come out of their ears. So the next node's previous is equal to the current. No. Next node's the current. Split screen mode. So this current is currently pointing at. That's sideways. So current is currently here. So what our code is saying is we're going to create a new node, and the new node's previous is set to Chris, new node's next is set to Lester, and then current points to next is this guy. Current points to next is this guy, right? Current points to next, and so current points to next. His previous is set to be Emma. And then current's next, Chris's next, is then set to be Emma as well. And so what this is doing is, before we had Chris and Lester like this, and instead they're now like this, and hers are like that. And then we update the size, we're done. However, just wrapping your mind around this is like the hard part, which is why I've been giving you guys 2 weeks of Zybooks on the subject to try and mentally prepare you for doing this. The terminology is different in Zybooks, by the way. They use append, like Mr. Shahab, I think, was asking. So, what's up, girl? So, that's it. Now we need to worry about tail. So in the case of tail, what do we need to do? So let's come back into OneNote. Let's try and visualize this. It's always a good idea to visualize it first. So let's say we've got 1 and then 2, and now we're going to be appending here, right? So head is currently here, tail is currently here, 1's next is that way, 1's previous is pointing at null. Come here, sweetheart. No. 2's previous is pointing at 1. 1's previous is pointing at 0. The null, maybe I shouldn't use the numbers, whatever. 1's next is pointing at 2. 2's next is pointing at null. This is the tail, this is the head, and we're going to be inserting at the end now. So the only difference from what we had before was that we can't set next's previous, right? Because that will segfault. So for tail, what we need to do is we're going to new a new node called 3, I guess, very creative. We need to set 3's next to be null. We need to set 3's previous to be tail, and tail's next needs to be mouse. tails next needs to be, or we're going to call this guy current, whatever. Because current is going to be pointing here. Right? So his next needs to be set here, and then tail needs to move here. So how many different things is that? We have to new this, set its next to be null, set its previous to be current, set current's next to be this guy. So all that's the same, except we don't have a Lester in this case. So that's not gonna change. That's not gonna exist. And then instead of that, we just set tail to point to the new end. Okay. Okay. So we're gonna y and key. That code should be the same. New person is equal to new node, and so current is going to be the current end of the list. Current points to next is null. So actually, I can just pull this out, put it up here. Save us a little bit of redundancy. All right, so these can be pulled out as well. So the only difference is going to be tail is now equal to new person. No curly braces. One line of code. There. Anytime you have statements that have duplicate code, you can usually pull it out. Stuff like that. So this is going to create a new person, and it's the same either if you're at the tail or in the middle. You pass in the data that you're going to store. Its next pointer is equal to the current person's next pointer, which may be null, and that's fine. You can copy a null pointer, that's fine. And our previous is always going to be cur, the person we just found. If we're currently at the tail, then the tail points at the new person. Otherwise, the person after us in the list, their previous pointer is set to be the new person. So that's the only difference. You have to special case the tail. So if you're at the end of the list, there's a null pointer there. If you did that and that's a null pointer, then dereferencing it would segfault. So you have to handle the edge cases like that. Okay. So, and then the current person, the current's next is set to the new person. So that's it. That is a insert function. So g++ main.cc, run, and you can see that Emma is in fact appearing after Chris Johnson now. Okay. So cool. And we can come down here and arrow the hills at the front. So let's after we do that, let's add somebody after arrow of the hills. Who on Discord wants to be invited to my wedding? Oh yeah, all right. Okay, so this is going to put Nick after Aaron, but then it's going to put Yochtheimer after Aaron as well. And so the Yochtheimer is going to come before Nick then, right? And then it's going to put Bazookian before Yochtheimer. So it's going to be Arrow of the Hills, Bazookian, Yochtheimer, Nick Muya, Chris Johnson, Emma Scandon, Lester Ederlin, and Mr. Wolf. Okay. There we go. Okay. You're welcome, Master Crash. It's a good name for today's lecture, Master Crash. Because if you screw up any of these things, you're gonna have a bad time, right? So let's say that you guys screw up. Let's say you do this first. Cur points to next equals new person. When you do that, it's gonna jack it up, right? Because you've screwed up the next pointer first, right? And so you're setting new person's previous pointer to be itself when you do it that way. So, yeah, you gotta. In that case, you actually probably wouldn't notice it because we never print the list backwards, so you wouldn't even know. You wouldn't even know necessarily that the previous pointer is broken unless you do something else with it. You know. Tragic Crash is the name of my new band. Yeah. Okay. And so it's really important that you draw pictures of the linked lists, and just every time you erase something, that's a line of code. Every time you draw something new, that's a line of code. And yeah. And hopefully the Xi books that I've given you will help conceptually with it. Oh, your new stand. Yeah, nice. Nice, very nice. My stand is the world. All right. Deleting is pretty similar to this. There's just a couple extra edge cases you have to handle, because you can delete the head, you can delete the tail. You can delete both the head and the tail at the same time. You delete from the middle. So, same idea though. You know, just sketch it out, see what pointers need to change. If you were to delete 2 here, 2 gets erased, and then you can see which pointers need to change, right? So those pointers are gone. What pointers need to be cleaned up? You can just look at what pointers need to be cleaned up if you're deleting from the middle. What do you guys see? Are there pointers pointing at nowhere now? Right. You have no idea what JoJo is? All right. Yeah. That's fine. What pointers need to be cleaned up? What do you guys think? You're very much not aware. Good for you. All right, so this guy needs to be cleaned up, and that guy needs to be cleaned up because they're pointing at the corpse of the old one. So this guy needs to point over here, and this guy needs to point over here. So you need to figure out how to do that. And then you're good. Size minus minus, good to go. Okay. So whenever you work with linked lists, just sketch it and just understand pointer notation, understand the arrow thing here. If you can wrap your mind around that, then you're good. Okay? That's as hard as it gets. Any difference on linked lists on asymptotic analysis? There's no asymptotic analysis here. If you're talking about like big O notation, find is big O n, because it's, you know, this is big O n. InsertAfter is big O n as well. Why? Because it has to, it's searching through the linked list to find the person, and once it finds the person, it inserts after. Pushback is order 1. All the other pushes and pops are order 1. If you had a pointer, though, if you had an intrusive linked list, and you had a pointer to an element in the linked list, then you can insert in order 1 time. If you had a pointer already to the place where you want to insert, then you could insert in order one time, because you don't have to scroll through. You don't have to do this, right? You don't have to go through the whole linked list finding it. If you have a pointer there already, if cur is already set to wherever you're going to be putting it, then you can get rid of that order n loop, and you don't need to do that either, and it turns into order one time. So it's order n if you don't have a pointer to the place you will insert. It is order 1 if you have a pointer to the place you will insert. So asymptotic analysis means that you average the running time over a lot of runs, and that's important for cases like vector pushback, because vector pushback every so often will do an order n operation, but we call vector pushback order 1 asymptotically because it does an order n operation once every n times. N divided by n is 1. If you look at CPP reference, you will see that the insert function has different options. And the options, though, all take pointers. Okay. So given a pointer, insert a value at that pointer. Okay. Given a pointer, insert a value at that pointer. Given a pointer, 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 right? And so the running time of this is constant. Okay. These are linear because it's inserting multiple values, right? So if you're going to insert n values, it's an order n operation. But the standard library insert is order 1 because it only takes a pointer, technically an iterator, to the spot you're gonna put it at. So if you wanted to do what we had here, you would combine it with find, right? And so you would use std find. Let's see if they have a special one. No. Come on, new mouse, you can do this. Std find will search through any standard container class, like a list. It'll search for, Yoxtham or whatever, and then it returns a pointer to it, or an iterator technically. Okay. And then you can use that result to insert at that point in the linked list. So if you're going to do this with the std list class, you do a find first, then a list insert. Yeah, we're done, Emma. We're done. Just answering questions. Okay, so good luck on EU4. Nick is always happy to answer questions, especially at 7 o'clock in the morning. Make sure that you send him. Make sure you at Muya at 7 o'clock in the morning. That's when he's at his most active, his most awake. Make sure his phone starts beeping at 7 o'clock in the morning, so he is up bright and early. And tell him I said hi. What a funny guy. Would it be possible for you to push out the code from today? Sure, why not? I mean, I'm basically doing most of the homework assignment for you, it feels like, but sure, why not? Copy main.cc into /public /linked list.jpg. Not JPEG. That's what's linked list.cc. Okay. This, of course, stands for the California Highway Patrol. Right? So copy /public /linked list.cc to your home directory or whatever. There you go, and that'll give you a copy of the source code that I did from today. Okay. All right, so that is it for today, guys. We got IS-50 right now, so I need to switch gears and start talking about video games, video game development, stuff like that. CHP, yeah. It's an alias I've set up that makes my public directory public again. So, EU4 is greater than UE4. That's fantastic. That's great. All right, cool. I'll see you guys.